To be fair concerning the differences between my universe and the FLRW1, the main one is that special relativity is preserved through the design of the four-position tensor. As well, the gamma connection coefficients are nearly all equal except for appearances of the Hubble parameter. Mine is half what you would expect in the case of the FLRW metric. At the same time, the component gamma 000 is not null in my universe. In fact, the gamma 0 mu nu components form a Minkowski metric multiplied by the half Hubble parameter I mentioned previously. So, now that we established that in this case, the universe has a Lorentz factor as a spacetime interval, we are bothered because we lose the possibility of a horizon, meaning that all light is supposed to reach us somehow. So, how do we retrieve a horizon in some way? The idea I am thinking about is to think of an observer far away from any mass, at instant t, with a given scaling factor a. Now, the horizon should be at some earlier time t0, which is reachable backwards in time through some curve we need to choose. We will just do guesswork and see if the result is satisfying. The basic idea I thought of is to have some curve which has an interesting arc length formula which ties nicely the formula of the curve with the formula for the ultra speed. The basic idea is that the furthest one can see should be at the meeting point between my newly introduced function and the scaling factor. This signifies that the meeting point would have a clearly defined arc length from present time, that is supposed to signal the observed age of the universe, while coordinate time allows you to know the absolute age of the universe, since it was of size 0. You can see here the guesswork, or numerology, that I played around with. My universe has to look nice. It is the most important requirement. Moving on, I am thinking of what would happen if your conditions tend to blue shift light. I am guessing that not only is light blue shifted through your radial gravity, but your horizon would need to be extended. At least, in terms of available technology, you would at first be able to see more photons than in minimal acceleration. So, I calculated the limit of the expression of our curvilinear aiding function for its parameter theta, tending to 0. It happens that the curve becomes completely flat and connects you to the origin point. This is expected to typically happen for a black hole, where I imagine the idea is that the light it sees coming from the horizon is the light of the Big Bang itself. In my universe, getting closer to the black hole, you would be able to be in an extremely expanded universe. So, if the coordinates we are living in are infinite, your horizon would become infinitely far as well, and you might even be able to see things that took place when the universe had an imaginary scaling factor. Remember what we said about this? We'll talk about it eventually because that period is rich with events where the actual moments that are related to matter or radiation domination can be found in those regions. Let us meet at the other side of the redirect, if you are watching this late enough. Or let us maybe wait for the next upload. Remember, all episodes are ready to be uploaded. You can subscribe and activate the bell to be notified as soon as the next video hits YouTube, or you can maybe miss an opportunity to be updated. I plan to make sure that the guesswork is not just that. My intuition will be my guide, and math will correct it.